Okay, so here we have a spring and mass system that's oscillating up and down. Whee! And it's supposed to measure every 60 minutes, or say every 60 seconds, but only 53 seconds have passed. And so we're trying to figure out, okay, obviously if we add more mass, then the system will run slower, because we want it to go slower because it's really only measuring 53 seconds and it's telling us that it's going 60, right? So we want to have an appropriate mass so that it is actually going every 53 seconds. So yeah. So anyways, we need a bigger mass. So the way we're going to do this is by first starting with the period of a spring and mass system. Okay, and we're going to start with this. All right, now there are two ways to do this problem. One is the kind of easy way, and one is the really easy way. So I'm going to show you the kind of easy way, but not actually take you through the calculations, and then I'm just going to actually solve it using the really easy way. So here is the kind of easy way. What you could do is you have enough information to figure out what the K value is of the spring. Because think of it this way, we're going to have to design a second clock that has a different mass. But you can't do any calculations if you don't know what the K value of the spring is. So what you could do is you could solve for the K of the spring. Because remember, you're not changing the spring, you're just changing a different mass. So you could do this. And figure out that K is 4 pi squared m all over t squared. Okay, and now that you have that, you could solve for a new m to get you the 60 seconds that you really want. And again, notice it's not really that difficult to do this, but there's an easier way. So that's what I'm going to show. So to summarize this way one more time, start by getting the K value. Where this one was 53 because that's what it accidentally is. And then you can put the K value into here now, and then put this at 60, the correct time at 60, and then solve for your new M. All right, that'll get you the right answer every time, and it's kind of a straightforward way to do it. And I bet you anything, 9 out of 10 students would do it this way, and they'll get the right answer, and they ace their test. Okay, but there's another way to do it, which is if you think to yourself, you're not adjusting the K value. The 2 pi is just a constant. All you're going to do is fiddle with the m. So what is the relationship between the period of a spring and mass if you keep everything else the same except for the m? Well, the period is proportional to the square root of m, right? Because if you keep everything else the same. Which means that the period squared is proportional to m. So you can actually just jump into something like this now and say, all right, I'm interested in ratios here. If I am interested, let me just write it out. So this is the ratio of the times. We have what I want versus what I have. And that is going to be equal to what you want over what you have. Now, if you do it this way, you're just going to be cross-multiplying, right? So it's going to be 60 squared 0.25 equals 53 squared m. So you end up with 60 squared times 0.25 divided by 53 squared. You get m is equal to 0.3204. Okay, so this is a ratio, by the way. This is a ratio. Sorry, let me rephrase that. We used ratios to get the new mass. Yeah, this is a ratio. This is a ratio. And by using the ratios, we can figure out what our new mass would be. And the mass, what we want, is going to be 0.3204 kilograms. I did double check this using the other way, and you get the exact same thing. So either way, you get the right answer. Okay, so what is the amplitude of the oscillator shown above? Remember that the amplitude is the midpoint between the max and the minimum displacement, which is another way of saying if you take this and this, what is the midpoint between those points? So here, well, I guess it's kind of, they kind of gave away the farm here because I already set the amplitude, the equilibrium at 0. And so since the equilibrium position's at 0, it makes the math really easy because it goes up to a +3 and down to a -3. You could figure out the total distance is 6, and the midpoint would of course be halfway between those things, and so the amplitude would be 3. I just explained the same thing 2 different ways, but of course the amplitude has to be 3 because it's 3 this way and 3 this way. All right, questions 6 and 7. These are conceptual questions, so I like these. They're easy to answer. Here we got a mass and spring system moving at an amplitude of 2.5 centimeters and a frequency of 26.1 hertz. Really quickly, if you're not familiar with it, the frequency is equal to the inverse of the period. And I'm just going to throw it up there. Remember, the period is equal to square root. This is spring and mass, so it's going to be m over k, which means that the frequency, again, if you wanted to calculate it, it would be k over m. Okay, what I'm trying to say here is that both the period and the frequency are only dependent on k and m. No other variable makes a difference. Notice that if you change the amplitude, well, where is the amplitude? It's not present. So the amplitude has no effect on the frequency, and it's the same thing with periods. Same thing with pendulums, by the way. That if you pull a pendulum back here and record the time it takes to go forward and back, it's the exact same time it takes to go even a further trip. It just goes faster. So the amplitude, what is the new frequency? Well, it's just this 26.1 hertz. It doesn't change. Number 7, the friction on the damp-driven oscillator increase. How does the resonance frequency change? Okay, so we've been doing a lot of spring and masses. I could show this with a period and pendulum, the period of a pendulum, or I could show it with a spring and mass, but let's just say that you start swinging at an amplitude like this, right? And so that means it goes similarly up to here. Now, there's going to be friction at the pivot point, so maybe when it comes back, it only goes to here. And maybe when it goes further, you lose more energy, and it only goes to here. And then you lose more, and it only goes to here. Right? So you can sense that, you can see that this thing was going like this, and then it kind of goes like this, and it kind of goes like this, and then this, and then this. You get what? Okay. In this case, remember, the period of a pendulum is only dependent on L and G. Right? There's a 2 pi in there, by the way. I'm just saying this is a sign for proportional. The period of a pendulum only depends on L and G. Now, just because something's losing energy because of friction doesn't mean that G is changing. And you're certainly not changing the length of the string or the rope. So does this dampening oscillation have any effect at all on the period? No. And if there's no effect on the period, that means there's no effect on the frequency. So that's how you want to think about it. And I could have done the same example with a mass and a spring, and I would just say the same thing. Has the mass changed? No. Has the stiffness of the spring changed? No. So then if M and K haven't changed, then the period or the frequency of a spring can't change, and so there you go. There's no change in the frequency. Okay, so here we've got a carbon-hydrogen atom. We will assume that the carbon here is stationary, and that the hydrogen atom is going to oscillate back and forth because of its bond, its chemical bond with, or I guess the atomic bond with carbon. So what we're trying to do is figure out what is the amplitude of the oscillation, meaning, basically how far down or up will it oscillate. Okay, let's just start with, we're given the frequency of the system, which is really, really important. So the frequency of a spring and mass system is 1 over 2 pi times the square root of k over m. That's just the inverse of the formula for the period, because the frequency is 1 over the period. Okay, that's where I'm getting it from. So we are trying to figure out, well, let's just start from here. We are given the frequency, and we are given the mass, which means we should be able to figure out the K value. Remember, we're approximating this oscillation like a spring, and so the K value isn't really like a spring, but the system behaves like it. So even though there's no real spring, we can still calculate a K value. I'm going to do question 8 all in algebra, just because the numbers get very, very ugly and very, very big with their exponents, being that it's subatomic physics. So anyways, the physics I'm going to show you is going to be algebraic, and then it's just at the end, it's just going to be up to you to plug in the numbers and hit enter. So we're going to solve for K right now, which means that 2 pi f equals the square root of K over m. Let's get rid of the square root. So 4 pi squared f squared equals, I hear my daughter screaming upstairs. Apparently she doesn't want to go to school. So square root of K over m, which means that 4 pi squared f squared m is your K value. And again, those numbers are going to be ugly. Those variables are kind of big, but we're just going to leave it like this. The potential energy of a spring in mass. Now she's stomping her feet. I can hear her upstairs. The potential energy of a spring is 1/2 kx squared, where x is the displacement, right? Ooh, whoa, that was bigger than I thought it was going to be. Well, I'll just rewrite it. So we actually have a K value now. We are given the potential energy, and we can solve for x. So the PE is the PE, and that says it has oscillating with an energy of this. So that is going to be the total potential energy at the end of its oscillation, right? Because at the end of its oscillation down here, it's all PE. There's no KE. So the 5.96 times 10 to the negative 20th, that has to equal your negative 1/2, and then 4 pi squared f squared m times x squared. And you are given m, you're given m, sorry, you were given f, you're given m, and now you can solve for x. They do want the answer in picometers. So whatever your x value is, you're going to divide that by 10 to the negative 12th, which will tell you the answer in picometers.